Okay, this will be our third and last video that is a preview to AP Stats, and we are going to talk about uh, collecting data a little bit on sampling design, and also going to do a little preview of probability. So in our book, this will be sort of a bit from chapters 4 and 5. So one of the things that we're going to do a lot in stats is what is known as sampling. So we're in essence going to have some population of that we're interested in. This population could be people, animals, or things. It's just a group we want to know something about. And so let's say it's could be every citizen, every voting age person in the United States, and we want to know the percent, a proportion they're going to vote for a candidate, or we want to know the average amount of time they sleep each night. We could do a census of all of them. But what we do a lot of time, and a census just means to, in essence, survey everybody in the population. And what we do a lot of time is take a subset of that we call a sample. Now, it's critical, though, that that sample, that subset of that, be representative of it. And so the big way that we get a representative sample is by taking what we call a random sample. Random just means everybody in the population is equally likely to be chosen. So, and like I said, population could be people, animals, or things. Could be people, could be things. Could be, the population could be every tree in the forest. And then we randomly select 100 of the trees to actually study. Or it could be, it could be there's a truckload of potatoes that's our population. There's like thousands and thousands of these potatoes on this truck, and we want to know their average weight. Well, we don't have time to weigh every potato on the truck, so we take a random sample and measure, 50 of them or whatever. So the first thing that I want to really talk about is that you've got to be able to describe exactly how you are going to get a random sample. And it's not a hard thing to do, but you have to know the proper terminology in order to do it. It's a frequent question. It'll just say, describe how you get a random sample. So let's look at this. It says, a school administrator wishes to gauge the opinion of the students of the school about a change in the policy that requires all students to have a physical education class period every day. She wishes to estimate P, the proportion of all the students that are in favor of this policy. So she's estimating a proportion. She wishes to take a sample of 50 students. There are 2,000 students at the school. Now, if she wanted to know the actual value of P, she could take a census of those 2,000. But for whatever reason, she doesn't have time to do that, so she just decides to take a sample. It's critical how she gets these 50 students if she wants an accurate estimate for P. All right, so describe a method she could use to get a random sample of size 50. And so I wrote out here how you would get a random sample. There's kind of different ways to do this, but this is sort of the main way. You have to say three things. First of all, give everybody or every animal or thing in the population a number. Secondly, using some sort of process to generate random numbers. That could be a random number table or random number generator. We'll practice that with our calculator. And then lastly, say that it's the people with those numbers that are in the sample. So you have to say those three things. It's not the numbers that are in the sample, it's the people in this case. So you would say assign all the 2,000 students a unique integer. And it's critical that you say the word unique or distinct. No one, you can't have two people with the same number. So you have to say they each get a unique integer from 1 to 2,000. Now the reason I put 4 digits here is a lot of times we're going to use a random number table, and so go ahead and put 4 digits like that. Okay, so it has to be, and say integer, by the way, or whole number. It's not just it's not a unique number. It's a unique integer from 1 to 2,000. So I number everybody in the population, giving them a unique integer. Secondly, using a random number generator, create 50. My sample size is 50 unique integers from 1 to 2,000. All right, and you have to say unique. We can't have anybody go twice. They have to be unique integers or distinct integers or 50 integers ignoring repeats. A lot of people will say it that way, but it's critical that you communicate that they're unique integers or that they're distinct or that you're ignoring repeats. And then lastly, it's critical that you say it's the people with those 50 numbers that are in the sample. So, and so that's how you do it. Another way, which I actually encourage this way more, is that what is known as the hat method. And the hat method just means create pieces of paper. So the hat method would be this. Take 2,000 pieces of paper, and it's important that you say the pieces of paper equal size and well mixed. That takes care of the randomness part of it. So write all 2,000 students' names on 2,000 pieces of paper that are equal size, well mixed. Pull out 50 pieces of paper. The people whose names are on those 50 pieces of paper are in the sample. That would be another way to do it, and I actually encourage that because people tend to mess up less on that. So that is just clearly stating how you would randomly select. All right, so now the next thing, let's look at this situation. All right, so instead of a random sample, the administrator decides to take a convenient sample by walking down to the gym at the end of the day and surveying the first 50 students that walk by her. Describe how this sampling method could lead to a biased conclusion. So bias just means they're systematically favoring certain outcomes in a situation. In other words, what we're doing here, we have a population parameter, P, that we're trying to estimate. P is the proportion of all the students that are in favor of the PE policy. And we are estimating that with what we call a p-hat. So bias is when there's something that is causing my p-hat to be a bad estimate for P. Now, I know that my p-hat, my estimate from my 50, is going to be off of P just because of sampling variability. But a biased situation means there's something systematically that's wrong. Whenever you have a biased situation, it's critical that you state which direction you think your p-hat, your estimate, will differ from your P, your proportion. Okay, and we'll do this with means later on as well, and other sort of statistics. But it's critical that you state how your estimate is going to differ from that, all right, as best you can. And so this is what I wrote. In this situation. All right, so the 50 students in this sample probably place more emphasis on the importance of PE than the rest of the 2,000 students, since they are all in the gym. So, all right, thus, the estimate from this sample, the p-hat, will probably be systematically too high as an estimate of P, the proportion of all the students who are in favor of mandatory PE. So what you've got to do when you have a biased situation is you have to clearly state how you think your estimate will differ from the actual proportion, from the actual parameter, and to give a why. And so that is that. All right. Context number 3 from data collection that I wanted to emphasize with you is this. All right, so this is a different context. All right, a doctor is trying to see if a new drug is effective in lowering cholesterol in patients with high cholesterol. He has 30 patients with high cholesterol take the drug every day for 2 months. After the 2 months, he notes that all 30 of the patients have significantly lower cholesterol and conclude the drug works. And that makes sense, I would think. Is that they all had high cholesterol, they all took the drug, and all their cholesterol went down. But in the world of statistics, we have what is known as confounded variables. Explain how the concept of confounded variables could cause a problem with the doctor's conclusion. So what a confounded variable situation. Let me draw you a little diagram. So what's happening here is we have this variable here is, in essence, they're taking a drug. So this is, the variable is, in essence, do they take the drug or not? Do they take or not? And that appears to be connected with lower cholesterol. Okay, there appears to be a causal relationship. But the problem in the world of stats is there could be another variable down here. There could be another variable that's messing with the situation. For instance, maybe they started exercising. During the time that they took the drug, they started exercising more. All right, that maybe they wanted to impress their doctor or the nurses there or something like that, but they started exercising more. Maybe it was the exercise that actually caused the lowering in cholesterol. So though it appeared to be the drug, maybe it was the exercise. This is what we call a confounded situation. We don't know if the lower cholesterol is due to the drug or the exercise. And so we say that these two variables are confounded. The answer to this situation, by the way, is doing what is known as a controlled experiment. And we don't have a control group here. In other words, we don't have a group of people that have high cholesterol that aren't taking the drug. all right, that are experiencing other variables the same, or possibly taking a placebo, but that's sort of a different problem. But this is the way I wrote out this confounded situation. And the key thing when you're describing a confounded situation is that you make sure and connect all three variables. Make sure and connect that variable with that variable with that, and that variable with that. And in this particular one, I went with a change in diet here, not with exercise. But, and so here we go. So there could be another variable that the 30 patients experienced that lowered their cholesterol. For instance, maybe during the time they took the medicine, the 30 patients all started eating better. So thus, I've connected the explanatory variable, which is taking the drug, with another variable, which is eating better. All right, wanting to impress their doctor. So I kind of gave a reason why that would happen. All right, maybe this better diet actually caused the cholesterol to go down, not the drug. So I've clearly connected my other variable with the response, which is what we're measuring, lower cholesterol. So in this case, we wouldn't know if the lower cholesterol was due to the drug or to the diet change, so those variables are confounded. So that is your little introduction to data collection, and that is the sort of reasoning that we go through in analyzing biased situations, analyzing situations where there's an erroneous causal situation there. So that is the sort of thing that we'll be looking at in that regard. And then lastly, the last thing I wanted to do for you as far as a preview is to preview a bit of probability. And so probability has a number of different fun types of problems. There's a number of different, I think, sort of fun different games and things that are involved in probability and the other, but it can be one of the more confusing areas. And so I wanted to bring up sort of a classic sort of a probability problem, and this one is one of the ones that we could use a Venn diagram to solve, but also we'll use our addition rule. So anyway, so let's take a look at this situation. So 12% of the senior class at a large high school takes AP Stats. 18% of the senior class at this school take AP Literature. 10% take both AP Stat and AP Lit. All right, if you randomly select one of the students, find the probability they take AP Stats or AP Lit. Now, whenever you're given, in essence, a situation where, you know, the probability of one thing, probability of the other, probability of both, a Venn diagram could come into play. But first of all, I want to do this, in essence, using the formulas that we have. All right, whenever in the world of probability, the probability of one thing or another, or means add. So, or means add. We're going to add those two probabilities together. But the problem is this. So our little notation here would be the probability of stats, and then or means union, and we'll talk about this notation later. So stats or lit is you would add up the stats. It's going to be, so that's going to be the probability of stats is 0.12. Or means add 0.1 or 0.18. The problem is, I just counted the people that took stats and literature. I counted them twice. In other words, the people that took both classes. So I've got to subtract them off once, and that'd be 0.1. And so that'd be 0.3, that would be 0.2. So 20% take AP Stats or Lit. And by the way, when it says one or the other, it means one or the other or both. Now, in that, you're going to have a little formula sheet, and that is the first formula on your little formula sheet with probability. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. That means an intersection there, which means and. All right, so that's going to be our first little formula. All right, so what's the probability that neither? Now, the probability of neither, that they take neither of them, is just going to be 1 minus the probability that they take either of them. And so neither is equal to 1 minus 0.2 or 0.8. So if 20% take AP Stats or AP Lit or both, that means 80% take neither. All right. What about AP Stats but not AP Lit? So what you would do there, and it is you would in essence go, well, the probability they take AP Stats is going to be 0.12, but you have to subtract off those that are taking an AP Stats and AP Lit, which is 0.1, and so that's 0.02. And at this point, I'm going to make our little Venn diagram. So our Venn diagram is this. is this rectangle is going to represent all of the students, all of the senior class at this school. That's my population here. And so this circle represents the percent taken stats. And so it says 12%, so I'm going to go 0.12. That sort of represents the area of that circle is 0.12. And then this circle represents the percent that are taking AP Lit. And if I was going to do it exactly right, it would actually be proportional correct, which this isn't. But anyway, it says 18%, so that's 0.18. So 0.18 represents the area of that whole circle. And then it says 10% takes both, and so that's 0.1. That is the overlap. So 0.1 in the middle there. And so what we'll do is I'm going to subtract off if 12%, if this area is 12% for the whole circle and this is 10%, that minus that is 0.02. That represents the area that's in the stats circle, but it's not in the lit circle. So the two parts added together add up to the whole. And the same thing here. If that's 0.18 and that's 0.1, if I say that minus that, so that would be 0.08. That would represent the percent that take lit but don't take stats. And so that's what this is. I'm sorry, I didn't put that problem on there. So anyway, okay. And so now, and then the last thing about this Venn diagram, what about the area of the outside? Well, the area of the inside, that plus that is 0.2, and the whole thing has to add up to 100%, so that's 0.8. So these four areas, that, and that, have to add up to 1. So anyway. And then, okay, let's talk about what is known as a conditional probability, the probability of they take AP Stats given they take Lit. And that, by the way, is the second formula in your formula sheet is A given B. That little vertical line segment means given. It's the probability of A and B over the probability of B, over the probability of the second one. Okay, that's our little formula for given. So if you run into someone, given they take AP Stats, what's the probability they also take AP Lit? So our little notation here, the probability they take Stats, given they take Lit, according to our little formula, is the probability of both of those things, Stats and Lit, over the probability of Lit. That's how you do a conditional probability. And so Stats and Lit, that's 0.1, over the probability of Lit, which is 0.18. And so that, in fact, let me see what that is. That's 0.1 divided by 0.18. And so that is equal to 0.5 repeating. 0.5 repeating. And then what's the probability they take Lit given they take Stats? Well, the notation there, Lit given Stats, is the probability of both of those things. The probability of Lit and Stats over the probability of what you're given, the probability of the second one. Lit and Stats, that's the overlap, that's 0.1, over the probability of Stats, which is 0.12. And so 0.1 divided by 0.12, and so that, in fact, is 0.83 repeating. So that's 0.83 repeating. And so those are what is known as conditional probabilities. And then lastly, state whether or not they're independent. Now, independent means this. They don't have anything to do with each other. In other words, the occurrence of one is in no way associated with a change in the probability of another one. In other words, if I told you someone took stats, you have no clue whether or not they take literature. It has no influence on it. All right? And so there's a couple of different ways that you could show independence. All right, and you have to memorize these formulas, by the way. If they're independent, well, let's just take this probability, this conditional. If they are independent, in other words, they really have nothing to do with each other, they don't influence each other at all, the probability someone takes Lit given Stats is just going to equal to the probability that they take Lit. It doesn't matter whether they take Stats or not. The probability they take Lit is just the probability they take Lit. It's kind of like independent events is like if it's going to array, let's say event A is that I go golfing today, which I'm going to do, or event B is whether or not it rains in Berlin, Germany. They're independent. It doesn't matter if it rains in Berlin. It's not going to affect whether I'm golfing. On the other hand, if event B is it going to rain in Huntsville, those events are not independent. If it rains in Huntsville, the probability of me golfing just went down a lot. And so if these events are independent, the probability of Lit given Stats is just the probability of Lit. Well, we just found that to be, so 0.83 repeating, that is certainly not equal to the probability of Lit, which is 0.18. In other words, what this is saying is if I told you someone took Stats, the probability of them taking Lit just went up from 18% to about 83%. So therefore, they're not independent. Of course, and the other way you could do is go in the other direction. If they're independent, the probability of stats given lit is just going to be the probability of stats. And so the probability of stats given lit is 0.5 repeating. And the probability that someone takes stats in general is 20%. They're not independent. That also shows they're not independent, because the occurrence of one changes the probability of the other one. If someone takes lit, their probability of taking stats went up from 20% to like 56%. And the last way you can show independence is by multiplying, and this is done a lot. If they're independent, you have to memorize this. If they're independent, the probability of one times the probability of the other is equal to the probability of both, stats and lit. So that is an important concept. If they're independent, the probability of one times the probability of the other is equal to the probability of both. Now, to show independence, you just have to show one of these things, by the way, but there's three ways of doing it. So that, in this case, that would be 0.12 times 0.18. Is that equal to the overlap, which is 0.1? And so in this case, so 0.12 times 0.18, and so that is equal to 0.0216. That is certainly not equal to 0.1. So therefore, they're not independent. So that's your stats preview. Obviously, we're going to talk about this during the course in full detail, but hopefully, exposing you to this stuff will help you understand it later on. Okay, thanks a lot, and we'll see you in August.